Hey guys, welcome back to your next math lesson. This section is all about Pythagoras' theorem. Since I use it in the next section, I figure we may as well make sure we know exactly what it is and prove that it's real and not just some kind of figment of our imagination. Okay, so to begin, Pythagoras' theorem says that when you have a right angle triangle, see if I can draw one, I always fail at these. Right angle triangle, that one's okay. Side lengths A, B, and C, where C is the longest side, the hypotenuse. Pythagoras' theorem, Pythagoras. I spelled it wrong in the next section. This is an A, not a U. I spelled it with a U in the next section. Anyway, when you have a right angle triangle with side lengths A, B, and hypotenuse C, Pythagoras' theorem says that it's always A squared plus B squared equals C squared all the time. That's it. That's the theorem. Pretty simple to understand. You've just got a right angle triangle. It has side lengths A, B, and hypotenuse C. And whenever you have this situation, it is always true that A squared plus B squared equals C squared. How did somebody come up with this theorem? I actually have no idea. If I had to guess, I would say that somebody plotted a circle on a graph. Somebody drew a graph with x and y axes, x, y, and observed that when you have the mapping x squared plus y squared equals r squared, if you actually plot this thing, here's r, negative r, r, negative r. By the way, r is bigger than 0. If you actually plot this thing, like we'll do in the next section, it looks like this. It makes a circle. Remember, what these points represent is like any x and y pair. If I put x into this function, into this mapping rather, we're going to find out it's not a function as well. If I put x into this mapping, then this is the y pair that goes with it. So this is the points x, y. And somebody observed that plotting this circle, if we make it into a right angle triangle, like this, then this length here is always r, because that's the radius of the circle. And so for this x and this y, it must be the case that x squared plus y squared equals r squared, where r is the radius of the circle and hence the length of the hypotenuse of the right angle triangle. Obviously this is a right angle down here. So that's how I would guess somebody came up with it, but actually I have no idea, and I don't think anybody knows exactly who the first person was to come up with it or how they came up with it. Okay, so next up, what we want to do is actually prove this thing. I can't use the circle in my proof. We can't use the circle in our proof because I'm actually going to use Pythagoras to show that this mapping here really is a circle. So let's come up with let's use another way to prove it. And there are 1,000 different proofs. This is what I'm going to show you is the one that always made the most sense to me. I find it just very easy to understand visually. So it works like this. You draw your triangle. This is the same triangle as before. It has side lengths A, B, and hypotenuse C. Sorry about the wonky line there, but you get the idea. This is a right angle triangle. Now what we do is we just take that triangle, rotate it a bit, and draw another one. So that the side length B is next to A, and this is side length A, and this is side length C. So we got B, A, C. Draw another one of them. This is side length B. Wow, I really made a mess of this drawing. This is side length A. This is side length C. So B, A, C. And finally, this is side length B. This is side length A. And this is side length C. So notice that corners are the right angles, and that B always goes next to A on the outside. And if I drew it properly, which I didn't really, but it's enough to get the idea, you should see that this thing makes a square around the outside if I lined everything up the way it should be lined up. So this thing actually forms a square. Now we're going to calculate the area of this square in two different ways. But first, I would like to make another observation. So we're going to call this angle X and this angle Y. Well, if this is angle X and this is angle Y, what's this angle here? Well, this is the same triangle except rotated. So this has to be the same as angle Y. And now I want to ask the question, what does X plus Y equal? Well, angles in a triangle add up to 180 degrees. This angle here is 90 degrees, and so 90 plus 90 equals 180, so we must have X plus Y is equal to 90. So angle X and angle Y, when you add them together, you get 90 degrees. So the sum of this angle here and this angle here is 90 degrees. So what about this angle here? How do I know this angle is 90 degrees, this angle in the middle? Well, this angle has to be 90 degrees because angles on a straight line add up to 180 degrees. So this is a straight line here. And if X plus Y equals 90 degrees, well then all that's left is this angle in the middle, and so it has to be 90 degrees because 90 plus 90 equals 180. Okay, so for that reason we know that our shape in the middle of this thing is also a square because its sides are all the same length. It's quadrilateral, it has 4 sides, and all of its angles, all of its interior angles are 90 degrees. So it has to be a square by definition. Alright, so we're going to calculate the area of the blue square, the outer square, in two ways. First way we're going to calculate it is the obvious way. Well, it's a square with side length A plus B, and so the area of the square has to be A plus B squared, because to calculate the area of a square, you square its side length, you times its side length by itself. So the area of the blue square is A plus B squared, but that's not the only way we can calculate it. We can also calculate it by summing together the area of the shapes in the middle. So we're going to calculate the area of this triangle. Well, the area of this triangle has a height of A, and it has a width, a base of B. And so the area of the triangle must be half times A times B. Well, we've actually got 4 of these triangles. 1, 2, 3, 4. So the area of these 4 triangles, since they all have the same area, it must be half times A times B times 4. Last but not least, we've got the area of the square in the middle. Well, the area of the square, it has side length C, so the area of the square must be C times C, or C squared. So adding together the area of those 5 shapes, 4 triangles and 1 big square, we get half times A times B times 4 plus C squared. Well, half times A times B times 4. 4 times a half is just 2. So this is equal to 2AB plus C squared. Okay, so right now what we have is A plus B squared equals 2AB plus C squared. Well, let's expand this out. A plus B squared is equal to A squared plus 2AB plus B squared. And we know that this is equal to 2AB plus C squared. Well, now the result is obvious. because all we have to do is cancel out this 2ab by subtracting 2ab from both sides. And so we get, finally, what we're left with is a squared plus b squared equals c squared. If you're confused on how I got this thing, remember, if you're confused on how I got this thing, all I did to get that was expand out these brackets here. If you expand those brackets out, you get a times a plus a times b plus a times b plus b times b, which is a squared plus 2 times a times b plus b squared. Okay, so that is the theorem. A squared plus b squared equals c squared. That's the thing we were trying to prove. Remember, we started out with a right-angled triangle with side lengths a and b and hypotenuse c. And we just played around with it a little bit and showed that it must be the case that a squared plus b squared equals c squared. So that's all for this section. Thanks for watching. See you guys next time.